In this lecture, we talk about the technique called the shooting method that is used for finding approximate solutions to boundary value problems. Suppose that the boundary value problem is given by the differential equation y double prime of x equals p of x times y prime of x plus q of x times y of x plus r of x, with the boundary conditions that y of a equals alpha and y of b equals beta, with a less than b. We are going to discuss two approaches for the shooting method. For both approaches, we partition the interval from x equals a to x equals b using the partition x sub 0 equals a, which is less than x sub 1, which is less than x sub 2, etc., 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 all the way to x sub n, which is equal to b. So we get as the approximate solution for the shooting method a set of discrete values y hat of x sub I, which will be the estimate for y of x sub I. Both approaches begin by converting the boundary value problem, or BVP, into a pair of initial value problems, or IVPs. Then we derive the approximate solution to the boundary value problem from the solutions of the initial value problems. For the first approach, the first initial value problem has y double prime equal to b times y prime plus q times y plus r, with y of a equals alpha. And instead of defining y of b, we set y prime of a equal to 0, so that we have a horizontal tangent at x equals a. We solve this IVP numerically using a method such as Euler's method, Hoynes' method, or some other related method. But before we apply methods such as Euler's method or related methods, we reduce the order of the differential equation to first order. We introduce the new function u equals u of x and set it equal to y prime of x. Then u prime equals y double prime, which is equal to p times y prime, or p times u, plus q times y plus r. We get the matrix system with the vector y prime u prime equal to the vector with components u and pu plus qy plus r. For the initial conditions, we have the vector y prime of a, or y of a u of a, equal to the vector alpha 0. From the application of Euler's method, Hoynes' method, or any other similar method, let y sub 1 of x be this IVP's approximate solution. The second IVP has y double prime equals py prime plus qy, but this time without the r term. The initial conditions have y of a equals 0 and y prime of a equals 1, so that our aim from a different starting point is tilted at 45 degrees. We also reduce the order of this IVP. We apply the same method that we used for obtaining y sub 1 of x, and call the approximate solution of this IVP y sub 2 of x. Then we assume that the shooting method's approximate solution, which we call y hat of x, is given by the formula c sub 1 times y sub 1 of x plus c sub 2 times y sub 2 of x, where c sub 1 and c sub 2 are constants. To determine c sub 1 and c sub 2, we first check the boundary conditions. Y hat of a is supposed to be equal to y of a, or alpha. Y hat of a is also equal to c sub 1 times y sub 1 of a plus c sub 2 times y sub 2 of a. Y sub 1 of a is alpha, and y sub 2 of a is 0. Therefore, c sub 1 equals 1, and y hat equals y sub 1 plus c sub 2 times y sub 2. If y hat is to be the solution to the boundary value problem, then y hat of b should be equal to beta. Y hat of b is y sub 1 of b plus c sub 2 times y sub 2 of b. We use the values of y sub 1 of b and y sub 2 of b that we found from solving the two initial value problems numerically. So we find that beta minus y sub 1 of b all over y sub 2 of b equals c sub 2, provided that y sub 2 of b is not equal to 0. The graph of y hat as a linear combination of y sub 1 and y sub 2 might look like the one being drawn on screen. Y hat will be the method's approximate solution if, for the final check, y hat satisfies the differential equation. Now y sub 1, y sub 2, and y hat are each made up of discrete points, but let's suppose that y sub 1 and y sub 2 are the exact solutions of their respective IVPs, so that we can carry out differentiation on y hat. So we plug y hat into the differential equation. We take the second derivative of everything in this equation. And so y hat double prime equals y sub 1 double prime plus c sub 2 times y sub 2 double prime. We are assuming now that y sub 1 satisfies the first differential equation, and that y sub 2 satisfies the second differential equation. Gathering the p terms, we have p times the quantity y sub 1 prime plus c sub 2 times y sub 2 prime. And gathering the q terms, we have q times the quantity y sub 1 plus c sub 2 times y sub 2. Then we have plus r. This is y hat. This is y hat prime. So y hat satisfies the differential equation with the correct boundary conditions, and the discrete version of y hat is the shooting method solution to the boundary value problem. For the second approach, we convert the BVP into the IVP y double prime equals py prime plus qy plus r with y of a equals alpha, but instead of defining y of b, we define y prime of a. Since we do not know the exact solution y of x, we guess the value of y prime of a. Actually, we make two guesses for y prime of a. Let g sub 1 and g sub 2 be the two guesses for y prime of a. We first apply Euler's method, Hoynes' method, or any other similar method to the IVP with y prime of a equal to g sub 1. For the initial guess of g sub 1, we can use the slope of the segment connecting the two boundary points. Reduction of order gives us the following equivalent matrix system. We apply our numerical method of choice. And suppose that we obtain the solution y sub 1 and approximation r sub 1 for y of b. If r sub 1 ends up being equal to beta, then y sub 1 will be the shooting method solution to the boundary value problem. Otherwise, we aim a second time, using a different guess g sub 2 for the value of y prime of a. We solve this second initial value problem with the same method that we used to obtain the estimate r sub 1 for y of b. Now suppose that this time we get the solution y sub 2 and the approximation r sub 2 for y of b. If r sub 2 equals beta, then y sub 2 is the shooting method's solution to the boundary value problem. If not, we apply linear interpolation to find what the shooting method's initial slope y prime of a should be. Using g sub 1, we found r sub 1. Using g sub 2, we found r sub 2. Using the correct y prime of a, we should get the correct y of b, or beta. Let the correct shooting method's value for y prime of a be equal to g. So playing around with ratio and proportion, g sub 2 minus g sub 1 all over r sub 2 minus r sub 1 should equal y prime of a minus g sub 1, or g minus g sub 1 all over beta minus r sub 1. From this equation, we get this formula for g provided that r sub 1 is not equal to r sub 2. We can also use a Lagrange polynomial to express g in terms of beta. Using Lagrange fractions, the viewer can check that g is also equal to this expression. To get the shooting method's approximate solution for the boundary value problem, we apply the shooting method a third time to the IVP, but this time with y prime of a equal to g. However, we can be more efficient by simply applying the same linear interpolation for finding g to find the different estimates for each y of x sub I. First, we call this fraction c, and this fraction d. Check that c plus d equals 1. Let's suppose again that y sub 1 is the exact solution of this BVP, and that y sub 2 is the exact solution of this other BVP. Let y be equal to the linear combination c times y sub 1 plus d times y sub 2. We show that y satisfies the differential equation with y of a equals alpha and y of b equals beta. We multiply by c everything in the first set of equations and by d everything in the second set of equations. C y sub 1 double prime plus dy sub 2 double prime is y double prime. On the right side, we have p times y prime plus q times y. Since c plus d equals 1, cr plus dr equals r. Y of a equals c times y sub 1 of a plus d times y sub 2 of a, or c times alpha plus d times alpha, and since c plus d is 1, y of a is alpha. Y of b equals c times y sub 1 of b plus d times y sub 2 of b, or c times r sub 1 plus d times r sub 2. We replace c and d with their respective definitions. Simplifying this, we should find that c times r sub 1 plus d times r sub 2 equals beta. And so, if y sub 1 and y sub 2 are the exact solutions of their respective BVPs, y equal to c times y sub 1 plus d times y sub 2 satisfies the main boundary value problem in this lecture. And we can use linear interpolation to find the shooting method's estimates for y of x sub I. If y hat of x sub I is the shooting method's approximation for y of x sub I, then y hat of x sub I equals c, which is this fraction, times y sub 1 of x sub I plus d, which is this fraction, times y sub 2 of x sub I, provided that r sub 1 is not equal to r sub 2.